Alright, now we're going to look over section 11-4 on analysis of variance. This is one of the last kinds of hypothesis and tests and sort of concepts we're going to look at. Alright, so a key concept is that this section introduces the method of one-way analysis of variance, which is also called an ANOVA, which is used for tests of hypotheses that three or more population means are all equal. Notice it's three or more. And because the calculations can be very complicated, we emphasize the interpretation of results obtained by using technology. And for our purposes, technology I'd recommend the most is the ANOVA statistematic applet. And just other key concepts, just keep in mind still that a small p-value, such as 0.05 or less, leads to a rejection of the null hypothesis of equal means, because the null hypothesis will always be that the means are equal. And then a large p-value, such as greater than 0.05, will fail to reject the null hypothesis of equal means. Then just of course you can always just look at more examples to try and get better understanding for these ideas in this section. Alright, now for part one. Alright, and just to actually define it, so the one-way analysis of variance, or ANOVA, is a method of testing the equality of three or more population means by analyzing sample variances. These are some notes here. One-way analysis of variance is used with data categorized with one factor or treatment, which is a characteristic that allows us to distinguish the different populations from one another. So again, there's something differentiating the three or more populations. And just a little side note here, it's important to keep in mind that we'll use sample means, and although they might not be exactly equal, we use the ANOVA test to see if the difference in sample means will be statistically significant enough to infer that the population means will or won't be equal. Since we focus on statistical significance for all tests and statistics, really. Alright, and then requirements for an ANOVA is that the populations have approximately normal distributions. Two, that the populations have the same variance or standard deviation. Now, this doesn't mean they have to have exactly the same variance or standard deviation, but they should be pretty close. And third, the samples are simple random samples of quantitative data. So notice this time we're looking at quantitative data again, where we looked at categorical in previous sections of this chapter. Next, the samples need to be independent of each other. The last requirement is that the different samples are from populations that are categorized in only one way. And the procedure you go through to test the hypothesis that all the means are equal depending on how many means you have. First, recommend using technology of some sort. For our class, what I recommend most is the ANOVA statistematic applet. Then you can find the p-value from that, then form the conclusion based on that if you're going to be rejecting the null hypothesis of equal means, or if you're going to be failing to reject it, and then think about what that means in context. And just a caution for when we do ANOVAs is when we conclude that there is sufficient evidence to reject the claim of equal population means, so we cannot conclude from an ANOVA that any particular mean is different from the others. And there are other types of statistical tests to identify which specific means are different from the others, but that's not something we'll cover in this class. So ultimately, you can say that not all of them are equal, but you can't say specifically which ones are not equal to the others. Alright, so now for an example here, notice this example deals with three samples that have different sample sizes, and usually it'll be best to have same sample sizes, but I'll show you two different examples here. And so we're using the performance IQ scores listed in the table below, and a significance level of 0.05, to test the claim that the three samples come from populations with means that are all equal. And so these are IQ scores from children with low blood lead levels, medium blood lead levels, and high blood lead levels. And so it's a lot of raw data there, and think about we've got the sample means and standard deviations as well as the sample sizes provided in a separate table here. And this information will be particularly useful because when we plug everything into technology, actually I'll get to the technology in a bit, but so first go through a requirement check. So the 3 samples appear to come from populations that are all approximately normal. And then the 3 samples have standard deviations that are not dramatically different. We can treat the samples as simple random samples, all good there. And the samples are independent of each other, and the IQ scores are not matched in any way, so they're independent, all good there. And the 3 samples are categorized according to a single factor, so low lead, medium lead, and high lead. So again, that's just the one like factor or treatment that's differentiating these 3 samples. Alright, and then again, the hypotheses are just null always being that the means are equal, and the alternative being that at least one of the means is different. And so we're going to use a significance level of 0.05, and we can use technology to find the p-value and such. These are some of the other technologies that are out there, which if you know how to use them, you're more than welcome to use them. Notice this one gives a test statistic, a critical value, and a p-value. And there are just some other technologies out there as well. But I'm going to real quick show you how you can use the StatsMetic applet to do this problem. So again, just a quick navigation, how to get to those StatsMetic applets. And then going down to here. Okay, and this applet that will be useful for this section is all the way at the bottom, ANOVA. And so for when you type in all of your information, there's going to be 2 main ways we'll deal with it. Is you can use the raw data, or you can type in the mean standard deviation. You can add groups however you need to. Now, because this particular example had quite a bit of sample data, and we were provided the sample means and standard deviations, I'm going to use that option instead. Which, to save time, I've already got that typed in here. And so all I have to do once I've got all of that typed in is just click Begin Analysis, perform one-way ANOVA, and it gives me that p-value of 0.02 and a test statistic of 4.071, which matched up roughly with all of the previous technology results. Alright, so because we got a p-value of 0.02, then this p-value is less than the significance level of 0.05, so we can reject the null hypothesis. And there is sufficient evidence that the 3 samples come from populations with means that are different. So we cannot conclude formally that any particular mean is different from the others, but it appears that greater blood lead levels are associated with lower performance IQ scores. So that's just kind of putting that particular problem conclusion in context. And again, just keep in mind that the differences in sample means were statistically significant enough to conclude that not all of the population means will be the same. That's just a general thing to keep in mind about this particular example, and just always thinking of statistical significance for these tests. Alright, just some notes regarding the p-value and test statistic. So larger values of the test statistic results in smaller p-values. And so the ANOVA test is always right-tailed. So similar to the goodness of fit and independence tests from previous sections in this chapter, they're all right-tailed. And the figure on the next slide shows the relationship between the F test statistic and the p-value. And so assuming that the populations have the same variance, or at least close, same variance or standard deviation, the F test statistic is the ratio of these 2 estimates of the variance. And this is mentioning the F test statistic here because if we do ANOVAs using a table and such, kind of do it the more old-fashioned way, there is a different table we'd use for it, which I'll show how to do that later, but that'll just be an optional thing. And let's see, just kind of, again, talking about the ratio of the 2 estimates of variance. So the ratios that go into an F-test statistic are the variation between samples, which is based on variation among sample means, and then variation within samples, which is based on the sample variances. And this is just a little chart kind of emphasizing some of those same points. So if the sample means are all close, that means you must have a small f test statistic and then a large p-value, which will lead to fail to reject equality of population means. If at least one sample mean is very different, then that means you'll be finding you have a large f test statistic and a small p-value, which will result in rejecting equality of population means. And see, this is just another some just kind of saying that the test statistic for an ANOVA is an F test statistic, which is equal to the variance between samples divided by the variance within samples. This will be more of an extension thing I'll go over in a little bit, though. And just another caution here, so when testing for equality of 3 or more populations, we want to just make sure to use the analysis of variance. And we don't want to use multiple hypotheses tests with 2 samples at a time, because if we increase the number of individual tests of significance, we increase the risk of finding a difference by chance alone. And so ANOVAs help avoid that pitfall. So that's kind of just emphasizing like the whole reason ANOVAs are even used in the real world is just because we want to try and avoid as much error as possible. Alright, now I just want to show another example here where the sample sizes are the same. And this is book example 1, so we're using the chest deceleration measurements from car crash test dummies below for an ANOVA test to see if the 3 samples came from populations with equal means. We're going to use a 0.05 significance level. So this is all the data here, and again, I'm just saying that the null hypothesis is always that the mean deceleration, force is equal to, is equal for the small, medium, and large cars. And the alternative hypothesis is always being that at least one of the means is different from the others. Now, this is one case where if I'm using the Statsminic applet, I can just type in the raw data, which is what I just went ahead and did here in a separate tab to save time. So this is all that same data just plugged in from that PowerPoint slide. So once I've got all that, I just click Begin Analysis. It generates a bunch of dot plots and some other stuff for me, but I don't need any of that for actually performing the ANOVA. Just come down here and under Perform Inference, just click on Perform One-Way ANOVA, and I get that p-value of 0.028, which is all I really need to make my conclusion. So again, p-value of 0.028, and so I reject the null hypothesis of equal means, since the p-value is less than that significance level. And just, again, we conclude that the different size cars do not all have the same crash force safety measurements. So keep in mind that we can't say all 3 are different from one another, but at least one of the 3 is different. So we don't have all equal means. Again, just thinking of the statistical significance. So thus the differences in sample means were statistically significant enough to conclude that not all of the population means will be the same. So again, based on this sample of 10 cars each from small, medium, and large, we conclude that the overall populations of small, medium, and large cars would not have the same deceleration force measurements. Now, again, all of those have the same sample size of 10, and technology is useful for an ANOVA test where the sample sizes are different or the same, like we did with both these examples. And then for actually doing the calculations, it's much easier when the sample sizes are the same, and it uses a different distribution, which actually I'll show that in a separate video for just an extension, if you want to see that. Now, just big ideas with this section is that I want you to take away is that ANOVAs are used to test hypotheses that 3 or more population means are all equal, just emphasizing that. And again, if we increase the number of individual tests of significance, we increase the risk of finding a difference by chance alone, and ANOVAs help avoid that pitfall. So, the whole reason ANOVAs are used. And again, just a big idea, we cannot conclude from ANOVA that any particular means are different from the others, but can reject claim of equal means between 3 or more means. Then these next 2 will just be for an extension video if you want to look at that as well. And so an ANOVA uses the F table, which is a different distribution, and calculations to get the test statistics can be challenging. then the f-test statistic is very sensitive to sample means, even though it is obtained through two different estimates of the common population variance. Then the next part will be for an extension video if you want to see that.